Today we're going to be discussing more of what some of the team has been doing. Our team is code-named Probe Lab because we're doing lots of probing in the IPFS and LPTP networks. And this is what we are going to be, some of the results that we're going to be presenting today. So I'm not going to present any of the results. I'm just going to give an overview of what we've been doing so far. And lead to the rest of the team, the speakers that are going to give you the important information, the actual results. So let's get started. What we want to do is actually data-driven protocol design and optimization. There is a lot that someone can learn when we're looking into the actual data from the network and how the protocols actually perform, compared to their specification and what we think, programming time would happen in the real. So our kind of motto is that you can't really improve what you don't measure because you don't know where are the bottlenecks, and you should measure what you think you have just improved. So if you apply an optimization to a protocol and you push it out to the network, and the network starts transferring bytes around, you cannot, unless you have the right measurement and monitoring infrastructure, you can't really say if the optimization that you had on your plan and you were expecting is actually the optimization that is seen as performance in the network. So that's what we're trying to do. Now, the end goal, of course, of doing measurements in the network is not really just measurements just for the sake, but it's not an end goal. So the end goal is basically to identify the problems and go and quantify how much space do we have for improvement, and finally design protocol optimizations. And of course, as with every other protocol in the IPFS stack and IPFS ecosystem, which is open source, we want our results to be open source as well. So one of the things that we want to focus on is make everything available, not only the results themselves, but also the scripts and the software written behind in order to get those results. This way, you and everyone else can go and reproduce the results and do your own experiments. Now, the workflow that we are kind of following is that we start with a research hypothesis or facts from the network. Then, based on that, based on what we want to do in the hypothesis, we design an experiment methodology, then experiment instrumentation, and then basically doing the experiment in the network. We get the results, and then we have to do some analysis to see if they are what we expected it to be, if intuitively they make sense. And if they don't, of course, we need to revisit step 2 or 5. If they do expect if they do show what we were expecting, then all good, we move to the next study. So the methodologies that we have used so far, there are 3 complementary methodologies. One is through crawling, through several crawlers that exist in the IPFS network, but we've written or enhanced existing ones, through probes, which is basically controlled nodes in the network, and through logs. So I'm not going to be discussing all of that in this presentation, but I can point you to where you can find relevant information. And of course, some of that are going to be presented by speakers later on today. So the continuous network monitoring, we have been using the mighty Nebula crawler, the author of which is right here, and we'll be talking later today. It's a very useful crawler that we kind of adapted, the features that the crawler has from previous ones in order to get some more information that was important to us from the network. So the crawler has been running since last summer. It's now perhaps above 10,000 crawls, but if not, it's close to that. And we did some analysis. Some of the results I'm going to present are from October of 2021, which is the blue stripe down there. Among other things, what we have found is that we've seen more than 200,000 peers, more than 2 million addresses, about 500,000 IP addresses, We've seen that the network is transferring more than 1 billion requests per week, it should say there. And we've seen that IPFS nodes exist in more than 150 countries and 2,700 autonomous systems, which kind of verifies the fact that IPFS is a distributed network. What the crawler, though, also does is that it's monitoring the uptime. And that was important for us because we didn't just want to see how many peers are in the network, but how much churn there is in the network. So the churn is when a node is joining the network and then it's leaving at some point, what's the time between those two things? And of course, then when leaving, when do they come back again? These are important for peer-to-peer networks. As some of you might know, the churn of the network is something that drives the decision for many parameters in the DHT or other protocols. So, some quiz time. Who knows what is the peer churn in the IPFS network? So, who can fill in this gap? 50% of peers leave the IPFS network after how many hours? 2 hours. Okay, any other takers? 12, 6, not 12, definitely not 12, unfortunately. Half an hour, okay, you're stretching it, yeah, but you're not far away, fortunately or unfortunately. It's about 1 hour. So those two are the closest. Of course, this varies between different implementations of IPFS and different also versions of IPFS. But yeah, there is lots of churn in the network, at least from what we have observed. So the cloud dependency, IPFS is a decentralized network, but how much of the, how many of the nodes run on centralized cloud infrastructure? Any guess? Percentage of nodes that are deployed on centralized cloud infrastructure. You all know what centralized infrastructure is. Sorry? 90. Oof, no. It's too far away. 60, I heard. No, it's not 60. 20, okay. Getting closer. Be ready to be surprised. It's about 3% of nodes that runs on centralized cloud infrastructure from our measurements, which we double-checked and triple-checked because, yeah, it was a little bit surprising to us as well, but it's definitely good news if you ask me, because it means that the community is putting up own infrastructure to host IPFS nodes, which is great. Final one, what do you think is this? Could be a nice logo, but apart from that, what is it? Okay, no one can guess. You must know, you're in the middle. No, it's the representation of the DHT routing tables. It's the IPFS DHT. A little bit more fancy representations, but basically, yeah, it's bullet that, okay, it's connected to others, but it's not shown here, is the routing table representation of nodes in the network, which looks pretty cool. I mean, there are some things that we also cannot really understand and we need help, but that's why we're here. So let's go on. No winners here. So let's start a little bit by, sorry? We don't know. Yeah, there is lots of clustering. We can brainstorm later. Yeah, exactly. Yeah, yeah. And there are some outliers, if you see up there or down there. That's also very weird. What are these nodes? No one talks to them. I don't know. Cool. Okay, so I'm going to do a brief overview of how the IPFS system works, at least from the lenses of the IPFS DHT, because this is going to influence a little bit what we're going to talk about next. So what is happening in IPFS when you want to, when you have a document and you want to share it with others through IPFS, is that you get the document, you hash it, as you know, you produce the CID, and then what you do is you create a small file that includes the CID and your own, if you're the provider, and your own address information, the peer ID and the IP address, and you put that in a small file, and you send it to the IPFS DHT. And then the DHT does its magic, and it's going and finding one node in the network, which let's assume is that one. Now, next what you do is you send that CID to your friend that you want to access the content. So they have the CID, and what they do is they use a protocol that is called BitSwap, and they're asking their basically immediately connected peers to ask whether they happen to have that CID, right? If the answer is positive, all good, they get the file and call it a day. If not, then what they do is they also go to the DHT and ask for this CID, and the DHT again does its magic and hopefully ends up to the same node. What this node, the yellow node, does is that it sends what is called the provider record, so this small file that you stored there, to your friend. Now, at that point, your friend has got the CID, of course, which they knew, but also your address information, the peer ID and the multi-address, the IP address, basically. So they establish a connection and they get the file. So that's what is happening at the high level. Now, there's 2 points worth highlighting here. One is that you don't upload the file itself to the DHT, you just upload the provider record that then points to your machine and others can come and take it from you. At least that's the base version, unless we add other bits and pieces on top. And the second one is that, as you know, you can get the file and hash it again, and then once you hash it, you should come up with the same CID that you requested for, and that says that basically the file that you received is the one that you have asked for and not something else. So that's it at the high level. Now, there are some opportunities that we've seen while playing around with, and understanding all the different steps that are involved. And we figured out that the provide process, so the very first step there, when you want to basically put the provider record to the DHT, is very slow. It takes tens of seconds, in some cases more than 100 seconds. So the hypothesis there was that there is some bottleneck in the IPFS DHT provide process, which we do want to improve. Why is that? Through measurements, we have found that although the overall process takes tens and hundreds of seconds, the nodes that we are finding, so that red node there, and all the rest, we're not finding one, we're finding much more than one, we're finding 20. All those nodes are being found within mostly less than half a second, right? So this leads us to think that there must be some wrongdoing there, because it takes an order of magnitude more to basically complete the process when we could be as fast as doing it in less than 1 second. So we're working on this. There is lots of documentation and presentations on that, and it's ongoing work on how to improve that. What I want to say by that is that as you start playing with the network and through measurements, you can find out important details and important optimizations about the project, about IPFS or any of the project that you're working on. Now, the second one is the lookup latency, in particular the DHT lookup latency. So the hypothesis there is that if we break down the content routing process which is composed of many, many steps, as we've seen in this previous slide, then we'll identify every bottleneck that exists. And that's very good because, applying optimizations, then we can find, and optimize the performance. So what we did is that we did a controlled experiment. We spun up several different nodes that are controlled by us, and published a unique CID from one of them, and then went and requested that from all of the rest. And that went around because other nodes then published CIDs, and then the rest requested that. So we repeated that several times, and finally there were more than 3,000 CIDs that were published, and almost 15,000 CIDs that were retrieved. So that's the kind of sample size that we are talking about. Now, what we found out is that around 80% of requests from EU, from an EU-based node, have been resolved, or at least through the DHT part of the procedure that I described in less than 500 milliseconds, right? And 50% of all the requests got through the DHT part of the resolution process in less than 1 second. So what does this tell us? Where is the opportunity here? If you see, the middle picture is just the DHT walk duration, the DHT part of the process, and this is what I'm talking about above. But if you see that on the left as you're looking at it, then you see that everything is basically shifted by about 1 second. So there is 1 second there, which is like, 100% more of the overall time, which should be down to something and decreases performance significantly. Now, this is the step on bit swap, so that's the opportunity here. The bit swap process that we said in the beginning, where you go and ask all your immediately connected peers, might take a lot longer, and unless it is very successful, it's going to delay everything by 100% of the time. It's going to double and triple the time that you need as a normal user, as a normal client, to resolve content from the DHT. So if our hypothesis is correct, then it means that we can see great improvement in the resolution process. So this is an ongoing study that we have. We're trying to figure out how successful is bit swap, if it's a lot or not, and what does this mean for the average user. So these are two of the studies that we did based on measurements. Again, what I want to highlight is that as you dig more, you find more optimizations. That's why it's great to do measurements, and you should do as well. And then some other studies are also based on measurements, and those I'm not going to go into any detail because I'm going to ruin the next speaker's presentations. We wanted to see the DHT routing table health, so how well instrumented is every routing table so that it can point to the right other nodes if you ask them for something, for a CID or a peer ID in the network. Great study, very detailed report there. You'll understand how the DHT works, which in great detail, which is not very easy. Then provide the record liveness. Again, we're going to have a talk in a little bit about that. The research hypothesis there was that if provide the records do not stay alive, then the content that is published in the network is not reachable, which of course is terrible, right? If you have a storage and retrieval network like IPFS, and you publish content and then suddenly you cannot find it, then it's not great news. So great results there, very encouraging. So did I have a third one? I think I had a third one. I skipped it, that's okay. Third one. So that pretty much concludes what I wanted to say as in, what we have been doing roughly. There are many more studies, so you can see what we are, the results, some of the results that I mentioned, but also many more in this URL, stats.ipfs.network. There are weekly reports there, very detailed, very interesting. Talk about the geolocation of users, rotating peer IDs, the churn of the network, of course, and a lot more. So go check it out. You can read pretty much, yeah, all of what I said in this recent paper that we have. You can find it online, of course. I'm going to share the slides. This is the CID that is on IPFS network, so you can find it through that. Yeah, so you can get involved. You can find lots of what we're doing in our Notion page, which is also linked from here. We have funding available through the radius.space platform. You can, yeah, go there and apply. You can follow most of what we're doing in the GitHub repository network-measurements, which is where we put our reports, which is where we put the requests for measurements, as we call them. And there are many, many that are open. Of course, you can go and work on some of them, or you can add your own ideas, right? So we are looking for, you know, things like, why are these lines there black? Okay, let's figure that out. Yeah, you can also find us on IPFS Discord under #probe-lab. That's where the team is mostly chatting. So yeah, join that. In the Probe Lab Notion page, you can also see the a board of the projects that we have with our current projects that are in progress, those that are done, the next ones that we're going to work on, and so on. So you can use some of the tools we're developing to do your own research. So one of the teams that is present here right now, they did this telemetry, they developed this telemetry tool that you can put on your IPFS node if you're running one. You should. And then you can start getting statistics out of this node, which is very useful. I think there is documentation on how to set up flashy Grafana dashboards as well, but that's the easiest part. How to do the telemetry is the most important one. What else? Yeah, and we'll ask you to get involved in another study that is going to be primarily presented on Sunday in the libp2p day. So the libp2p team, as you might know, has developed a NAT hole punching approach for libp2p. NAT hole punching is, yeah, one big problem that has not been solved in peer-to-peer networks. So the libp2p team now does have a solution, and we're going to be running a study where we're going to ask users, anyone in the community, to download a binary and run it, and then we're not going to get any of your personal information, of course, but we want to see what this is going to do is going to instrument that node, like measurements between your node and some of the nodes that our lab is running, to see if there can be NAT hole punching through your home network, right? Which is great. It's really going to improve performance a lot if we manage to get that right. So we're doing the measurement study for the libp2p team. So the experiment is going to run later on in December. But if you want, you can scan this QR code, which is going to take you to this Google form, and you fill it in, just your email or contact information, so that we can reach out to you when we have everything ready. And yeah, you're going to be able to download that little program, which is going to add this box glove there on your desktop. And yeah, participate in the study. Of course, we're going to make the results publicly available afterwards, so you're going to be able to use them. Yeah, analyze them, publish your own papers, or publish your own blog posts and reports. Did everyone take a picture? Sorry, it's too far away. Okay, yeah, I'll send the slides. I'll share the slides in the Slack channel of this particular track, so that you can do it from there right now. Cool, yeah, so that's it from my side. I'm very excited about the rest of the program. We're going to talk about some things I touched upon, but some others that I have not talked about. So yeah, let's welcome our next speakers. Thank you very much.